In the last couple of videos, I've looked at examples of principal components analysis, which is a multivariate technique for reducing a high-dimensional dataset to a smaller number of dimensions that is still able to explain as much of the variation in the data as possible. And so even though we're using a smaller number of dimensions to understand the data, we're still retaining the structure of the full, rich data set. In this video, I'm going to look at a different multivariate analysis technique called multidimensional scaling. And this is used on data where we have measurements that represent the dissimilarities between different observations. One way to think about this is to think about observations as having a measurement representing the distance between them. So it need not be a literal physical distance, but it might instead be, for example, with biological data, the value might represent two different organisms and how dissimilar those two organisms are. Where a large number means that the organisms are very, very different, and a small number means that the organisms are quite similar to one another. So that's the type of data that we're looking at here. The best way to illustrate this technique is to use data where we do have literal distances. And so in this data set here, we've got distances between European cities. So we can see the first 6 cities here. We've got the distance between Barcelona and Belgrade as 1,528. I'm assuming kilometers. Barcelona to Berlin, 1,497.61 kilometers, and so on. And the end result of a multidimensional scaling is often a map showing the results in a way where the physical distances on the map are closely mimicking the actual distances in the data. They don't match exactly, but the idea is if the 2 dimensions of the map are doing a good job of representing the structure in the original data, then the distances in the actual end map and the original data should be relatively close to one another. With physical distances, like in this data set, this type of analysis is usually very successful because it's doing exactly what it's set out to do. But this technique is more broadly applicable, as I say, to data where the numbers aren't physical distances, they're more measures of dissimilarity between objects or observations. So there's different ways of doing multidimensional scaling. The method that I'll cover first is called classical or metric multidimensional scaling. And this is a little more rigid a method of the 2 methods that we're going to talk about. The second method is called non-metric multidimensional scaling, and that isn't concerned about preserving the actual distances themselves, but instead it looks at the relative or the order of the distances between the different objects, and so it's a little bit more flexible. It can be difficult sometimes to get a non-dimensional scaling analysis to work. The coding is a lot more complicated, and the algorithms are a little bit more finicky to get to work. But if you can get it to work, it often gives a more stable and successful end result. So anyway, let's just run through the analysis to see what happens. Just as with principal component analysis, we can create a Scree Plot. I've got to do the analysis first before I do the Scree Plot. So I'm using this CMD scale function, and this does a classical or metric multidimensional scaling. Okay, now I should be able to run this without getting an error message. Okay, so this is a Scree plot like the Scree plots we looked at with principal component analysis, and for this example the first two dimensions together explain almost all the variance in the data, and the remaining, these three remaining dimensions, are explaining almost none of the variation. So a two-dimensional solution is going to be pretty good here, which is not unexpected because, as I say, we're dealing with actual literal distances between cities here. So of course a multidimensional scaling is going to be a two-dimensional multidimensional scaling solution is going to be pretty good. Okay, so what we can do is, so this function here, this CMD scale, performed the classical metric multidimensional scaling, and what it does is it creates different axes, if you like, or different dimensions or different coordinates. And so if we pick off the first two coordinates and then create a two-dimensional plot from that, we're essentially recreating a map that on the map that we're generating here, it should be the distances between the cities on this map should reflect the distances in the data if the analysis has been successful. One thing to notice here though is that if you know anything about European cities, the map is kind of backwards and upside down. Madrid should be to the west, and Istanbul should be to the south, and Stockholm should be to the north, and Moscow should be to the east. So I kind of need to flip the axes around here, which is fine for me to do because multidimensional scaling doesn't really know about which way is north and south and east and west in this example. All it knows is it has to come up with a solution where Barcelona and Madrid are pretty close and Rome and Stockholm are pretty far away, and so on. So if I just flip signs of the coordinates and redraw the map, things look a lot more like they should. So this is an example where we have a multidimensional scaling that does a very good job of representing the data as it should, because we're working with actual physical distances here. Okay, let's look at a different example. This data set is different colors. So these are different colors, and the measurements are representing people's perceptions of how similar or dissimilar different colors are, where a smaller number like the 0.18 here, so in general people perceive this color W434 to be similar to W490, whereas these two colors W434 and W445 are perceived to be very dissimilar. We'll see the actual colors in a second. Actually, sorry, I'm talking backwards. These are actually the similarities. So it's backwards from what I said. So if I just subtract all these dissimilarities from one, all the similarities, if I subtract them from one, I'll get the dissimilarities. So let's focus on these numbers instead. So a high number, W434 and W504, these are two colors that people perceive to be very different, whereas a low number, W434 and W445, these colors are perceived to be very similar. Okay, just like in when we looked at the cities, a low distance, a small distance between two cities would be cities close together, and a large distance between cities would be cities that are far apart. So that's how this works. You always want to create data that represents distances or dissimilarities rather than similarities. Okay, so we'll run the metric classical multidimensional scaling again. We'll look at a Scree Plot. Looks like the first two dimensions are going to be pretty good because the height of the bars in the Scree Plot drops off quite dramatically after the first two. And then what I'm going to plot now is like the map of the European cities, only I'm drawing a map of colors according to the first two principal coordinates, or the first two dimensions of the multidimensional scaling. So here we can see that we're getting results that make sense, okay, because we've got I've colored the points according to what they actually represent. So these were the codes in the data set, but the colors of the circles are the actual colors corresponding to those colors that the people in the experiment were told to compare, and it's looks pretty successful. We got all the blues over here, the greens over here, and the reds over here. So this is the metric classical multidimensional scaling result. Let's see how non-metric multidimensional scaling works. So, as I say, the coding behind non-metric multidimensional scaling is much more complicated, and so it can be a little bit fiddly getting this to work, and you kind of have to iterate. But in this case, we can get it to work. So this is it doing all its iterating and trying to come up with a solution. Looks like it's going crazy. Okay, it's finally done. And let's look at a Scree Plot. Okay, so this is the equivalent of the Scree Plot for this particular function, and this is telling us that one dimension is pretty good. The second dimension is a big drop off, so yeah, this is kind of interesting. One dimension is really pretty good here, but let's just go with 2 dimensions like we did before. This is a graph showing how well the 2-dimensional solution fits the data. So the idea here is that the red line and the blue points should line up, which they're doing pretty good here. And then let's look at the final result. Let's look at the map. Okay, so this is quite similar to the non-metric solution. This is quite similar to the metric solution. Here's the metric solution, but the metric solution is more restrictive. So if you can get a non-metric solution to work, it's often a little more flexible and a little more representative of the structure in the data. So let's compare this with, there's the non-metric solution. So same basic structure. We've got the greens in this corner, the blues in this corner, the reds over here, there's an orange up there, but quite similar. But yeah, in this example, I think both the metric solution and the non-metric solution are quite effective at capturing the structure in the data. So that's an illustration of multi-dimensional scaling. So we'll finish up this video series, and this will actually be the last video in the whole course. We'll finish up with the next video on correspondence analysis.